Okay, I've got the video recorder going now, so I'm going to jump over there. Just quickly show you what I want you to do now that you've either downloaded this electronically and will write on a tablet to do it, or you've downloaded it and then printed it. What I want you to do when you get done with it, though, and that's going to be not when you get done using it during the class. When we get done with class, I want you to pretend that now the time is up to work on the exam, and now you're going to go off and get it scanned and sent to me. So that's going to be around 4:20 to 4:30 time frame. So I want you to just set it aside, but this is just sort of a dry rehearsal just to see how it goes. And what you put on the quiz, I don't really care. It's just the idea that you're going to do some scribbling on it, and then you're going to scan it somehow or another and get it back to me. And I just want to see what kind of quality everybody's able to get, and I'll critique you only on your quality of the print job, scan job, if that's not sufficient. So you'll send it back to me like you send documents, like Will sent me his homework just moments ago. So I'm going to see it on the direct channel, and then I'll be able to take a look at it on my computer. Okay, so we'll jump over and look at that. And hopefully I can think clear enough. I've got my Jupyter QT console running here to do some side calculations. And looking at the number of quizzes that I have left, there's about 3 more quizzes that I have that cover all the way to the end of the semester. So we're definitely nearing the end. I can tell you that much. Okay, so this is a combination, well, this is still transmitter stuff with bandwidth for the first problem. And I see I have a typo in here that should say 2. The second problem is a demodulator for FM. So the first problem is a modulator problem. So we have a VCO that has a modulation sensitivity of 1 kilohertz per volt. The output of the VCO is 5 volts peak and a 1 ohm system, and it's at a quiescent frequency of 10 megahertz. The input is driven by a message signal having a low pass bandwidth of 12 kilohertz. We also know the peak deviation under the given M of t is 240 kilohertz. So this is not sinusoidal frequency modulation. This is just general frequency modulation. So that means we have to use Carson's rule. But as a starting point, we need to get D, and I guess I'll change to a different color. Can you remember what the definition of D is? It's the ratio of 2 numbers. Yeah. Well, it's not FM though; it's W. So both of you had things that were close. So it's going to be delta F over W, where W is the bandwidth of the message. So delta F in this case is going to be FD times, well, we're already given the peak deviation, so we don't really need to use FD in this case. We're just given that the peak deviation is 240 kilohertz. So let's just maybe talk about that for a second. Does that make sense? I've given you the VCO sensitivity of 10 of 1,000 hertz per volt, but we don't really have use of that in this case because we're already given that the peak deviation down here, get the right color up here. Okay. Well, the carrier amplitude is 5 volts, so that's where the 5 comes in. That's a different quantity. So if we had a carrier out here, according to the description we have here, we have 5 cosine 2 pi times 10 to the 7th times t plus some phi of t modulation. So what we'd have to do, what I'd have to have given you is another quantity. I'd have to give you what is the peak amplitude of the message. So I would have to say, what I would have had to have done in that case is I would have had to have said max of magnitude of m of t is something like 5 volts or 2 volts or 1 volt. And then you would have multiplied that by FD, and that would have gotten you the peak frequency deviation, delta F. Does that help, Colton? Okay, but in this case, you're given that. So I guess we could back out of here what that would have to have been. So maybe that's another side question that I could look at when we get done here. So we have 240 kilohertz times 12 kilohertz. So 12 goes into 24 twice, and then we've got the 0 there, so we've got 20. Peak deviation is 20. Deviation ratio is 20 in this case. Does everybody agree with that? Okay. So according to Carson's rule, the transmitted bandwidth B is going to be 2 times D plus 1 times W. So that's going to be 2 times 20 plus 1 times 12. Pen is stopping on me. So that's going to be 24 times 21. And I'm going to be real lazy. And I would suggest that you use your calculator if you have it, just so you don't make a mistake, or careless mistake. Yeah, it's in kilohertz, so I'm going to have to take that into account. It'll be in kilohertz when I get done. So it's going to be 200. Oops, I didn't do the right numbers there. It's going to be 21. No, it's going to be 24 times 21. So 504 kilohertz since that's kilohertz right there. So getting back to Colton's question about getting peak deviation from FD and the maximum of M of T, we could actually work that out. I could actually have made a side question and say, what is the maximum value of M of T? That must be 240 divided by what? If I know it, peak deviation is 240 kilohertz, and I know the sensitivity is 1 kilohertz per volt, so I divide that by 1. That would be 1 kilohertz per volt, and then the units would come out here to be something ridiculous like 240 volts, which is not really very practical. It's just the way I had the problem created. Does that sound reasonable? I mean, it's the 240 volts is not at all reasonable, but in terms of the numbers, it's reasonable. To make this more realistic, though, this probably should have been a sensitivity, just to modify this problem. This probably should have been a sensitivity in the neighborhood of 10 to the 5th, so it would have been 100 kilohertz per volt or something like that. Would have made this work out a little bit nicer, because then I would have divided 240 by 100 and I would have gotten 2.4 volts. But the bottom line is the bandwidth right here is equal to that, 504 kilohertz. And that's the two-sided bandwidth. So that's what's sitting centered on 10 megahertz. Now, to work part C, we just need to find the power in the carrier, and we're assuming it's a 1 ohm system, and we know it's got a 5 volt peak. So that's the easiest part of the three little parts here. Remember, the envelope of an FM or angle modulated signal is constant, so its amplitude is 5, and the power in a 1 ohm system is just going to be the amplitude squared over 2, right? So that would be 12.5 watts. I vaguely remember long time ago, my brother went to a small private school in Wisconsin. It's actually one of the sister universities or colleges to Colorado College. I don't know how it was that my parents would let him go to such an expensive school, but he got to do that. I went to a state school. But he ran the FM radio station on the campus, and I think his the transmitter power, it was a very low power FM radio station, it was a very small community too, was around 20 watts or something like that of effective radiated power. So this number sort of falls in that range. I think KRCC is more like 10 kilowatts or something like that, or maybe even 100 kilowatts. I don't know. Does anybody know? The only way you know that stuff is usually at midnight or something. They have to give their call sign, and they have to give particulars about the station, like where the transmitter is located and what the radiated, I think they give the radiated power. But okay, so now moving on to number 2. This is a receiver problem, and this is the block diagram that we had in the notes a few days back, showing an FM discriminator, and I say it's typically preceded by a limiter. So what's the purpose of the limiter? It gives clipping, but what is the purpose of the clipping? Why do we want to put clipping on there?
Specifics.
So I could write down here, I could say clipping to do something. Remember the types of discriminators we were looking at, most of them have some sensitivity to amplitude fluctuations on the signal. So if you limit the signal so that its amplitude doesn't fluctuate anymore, remember for angle modulation, all the information is contained in the phase, which is just moving back and forth inside the envelope. So it has a constant envelope. All the modulation is inside of that. And if you clip it, you don't lose any information, but you do remove any residual amplitude modulation that might be arriving on the signal. So clipping to, oops. So I would say clipping to remove AM. That may be present, and it's also going to gain level the signal too. It's going to keep it at a constant envelope. Okay, now we're going to consider what a particular discriminator characteristic The one that was shown in the book just is a constant slope that goes down to minus infinity up to plus infinity. Well, a practical discriminator is going to have some bounds on it. But the bottom line is the discriminator, just like you were learning about in the second homework problem that you're turning in, converts a frequency deviation into a voltage. So in this case, this idealized discriminator is going to output 2 volts when you deviate 10 kilohertz above the carrier, and going to output minus 2 volts, and then it's linear all the way through there. So that's our discriminator characteristic. So if we wanted to be in particular about what we were doing in the homework, we could say KD, the discriminator characteristic, is going to be 2 volts per every 10 kilohertz. So if I wanted to put that in terms of volts, I could just go 2 over so it's 200 microvolts. 200 microvolts per hertz would be the slope of that line, right? Because it rises 2 volts when the frequency deviates 10 kilohertz. That seems like a really tiny number, but if you put it into the context of a peak deviation maybe being 5 kilohertz, then that's not really such a small number. So it would be something like, I just did a side calculation over here. So I could go 5E3 times KD, and that would be 1 volt peak that I'd be getting out if I happen to have a 5 volt peak deviation, and that's actually a pretty large voltage at that point. So okay, so moving on. Does anybody have any questions on that? That really wasn't the problem worked. I just decided to talk about it some. So now we're going to assume that the carrier is frequency modulated with a sinusoid. The sinusoid is at 1 kilohertz. The deviation constant in the modulator is 5 kilohertz per volt. So now we want to sketch the output from the discriminator. So I wasn't even reading the numbers in the problem when I was doing the little example up above. I was just thinking in general terms. But so our message, we don't really have to integrate anything. All we have to do is just study what's going on here. And we know that the peak deviation that the transmitter is putting into the receiver is going to be FD times 1, because implicit right over here is 1 volt. So we're getting exactly 5 kilohertz. And so it is exactly what I said. Maybe my brain just was subliminal and I said 5 kilohertz. I don't know. But we already know what that answer is. 5 kilohertz means that the deviation is pushing up to here and then down to here. So that means the output's going to rise up to 1 volt and take on a negative swing of minus 1 volt. And it never hits the ends of the discriminator, where this discriminator is linear. So that should be the type of wave shape we get. And of course, I've got the frequency at 1 kilohertz, so I guess the period is 1 millisecond then. and it swings between 1 and minus, or minus 1 and 1.
You made this job.
I'm stuck with Lloyd. So much for getting my life back.
Any comments?
It's almost lunchtime. Usually in home by myself. But
The message is FM over here is 1 kilohertz.
Maybe the universe is showing mercy on me.
what's the location?
So the period of the message is 1 over that,
58 or out of County 5. First promising thing all day.
which is 1 millisecond.
We can push it back.
I'm good.
The 5 kilohertz peak deviation just tells us how much that message is pushing the carrier frequency above and below
Carry out.
the center frequency. And in this particular case, the center frequency, FC, didn't even need to be spoken about. Just, it's symbolic at this point.
Must be at lunch.
The FC? Well, it's necessary information to describe the problem, but you don't need to have a number for it, and I didn't give you a number for it, so, yeah. This problem up here was there to trip you up. That much I acknowledge. But, yeah.
Call it in. Do it. This is Officer Monson.
You're talking about kind of like what happened in the homework problem? Is that what you're thinking of? Yeah, yeah.
Wow, well, she's right around here.
Yeah, that's right. Yeah, this was just a simplification. But if we go on to the phase lock loop, which we're going to jump right back into, we know what the effective discriminator constant is in the phase lock loop. So I'm going to move in and talk about that, I guess, since I think that would be helpful at this point, to know that or review that. These days of digital signal processing, we have everything just sort of defined very precisely, like the way this picture is. But that homework problem that you worked with the RLC circuit, you can see that the numbers don't necessarily come out picture perfect because it has to do with the circuit parameters. And then, of course, there'd be losses in there. If you wanted to be really picky, you would take that inductor and add some series resistance to it because it's got finite Q and so on, and then that would change the amplitude, and it kind of goes on and on like that. So I say I could say many years ago I knew that I was still heavily in the analog side of thinking. These days, though, so much of it's done in software that there's almost no oddballish looking shapes. Everything kind of is defined nice and neatly. But that doesn't mean everything always has to be like that. And for those of you that are in the comm lab, remember you worked with the radio boards, and those were RFICs, but they had an external discriminator tank circuit for the quadrature detector, FM detector that was in there. And that gave some discriminator gain constant, but I don't remember what that was. I think you read in the data sheet for the chip, and it gives you approximate values for KD, probably with a certain type of inductor that you'd put on there external to the circuit. And then if you wanted to really know what it is, you'd have to go in there and measure it by using a sinusoidally modulated carrier and then taking a measurement with the oscilloscope on the output of the quadrature detector. And I think that's kind of where you're at in your question, John, because you're thinking analog, or you were thinking analog, which is fine. Even though I'm an older engineering professor, there's a lot of things about analog I really like. Maybe it's because I grew up with it. For you guys, I don't know what you really like, because I sometimes see that circuit theory doesn't really turn a lot of people on anymore. But I don't feel sad about that. Dr. Kelker might feel sad about that because he teaches the analog IC course, and he's really an analog design kind of a guy. And there's a place for that in industry. There's jobs in that. There's jobs, there's all different types of jobs within electrical engineering. Systems modeling is what communications theory closely connects to, but you can be the implementer too. So I'm just kind of getting philosophical sounding, and you're probably getting bored with that. So I'm going to move back over to the lecture material. I'm going to also, I think, preview a little bit from the homework assignment. So right now, what I want you to do, whatever you've done on this quiz, just set it aside, except for Jared, who's got to take off somewhere. You can get to sending it to me on Slack since you're going somewhere. But take care of getting it scanned and sent to me when class is over with, just as the practice, and then I'll have some sort of a idea of how long it takes everybody to do that too. So I'm going to move over to, before I get back into phase lock loops, I'm going to look at the homework. So Colton, thank you. You must have done it electronically or something, but I don't want you getting distracted to take pictures. But if you got the picture quick enough, that's fine. So this next homework assignment has got a frequency synthesizer on it, which we haven't talked about yet. And that's one of the problems it's due. This is actually a very simple problem once we go through it. Second problem is working with a simulation. It's going to be working with the complex baseband simulation, which we hadn't quite gotten to in the Jupyter Notebook, but it was coming up very soon. And you're going to be characterizing the closed loop frequency response of the loop by doing some experiments to get there. And I'm going to kind of play around with that some today in the notebook, even though I'll probably do it again next Tuesday. It gives you an opportunity to get hands-on playing with a phase lock loop simulation engine. And the one you're going to be working with is one that's in Scikit DSP-com.synchronization. And we'll look at it. I've got examples for that in the Chapter 4 Jupyter Notebook. Third problem is just analyzing a simple low-pass filter and going through the closed-loop transfer function analysis like we did for the first-order loop last time. And then you're going to do a little bit of analysis in Part B, and that's very similar to what we did for the first-order loop. And the hints are thrown down here, but I'm not really going to get into looking at those right now. The hardest problem, though, is number 2, the simulation problem, and I'll maybe refer to these later when I start talking about it. Okay, so what I wanted to start by doing was just going back to the first order loop, and then we're going to move our way into the a form of second order loop. And then we'll do some experiments, and then we'll eventually move on to talk about indirect frequency synthesis, which is that first homework problem. So one of the things I want to come back to is just revisit this idea for the first order loop. It said that when you put in a frequency step of delta of omega and you have the loop's closed loop gain, which is the gain constants all the way around the loop, KT, the arc sine of that is the steady state phase error. And we got a chance to kind of see that in this picture up here. When we see that if the loop has got a delta of omega put inside of it, the loop will lock, but there'll be a bias that's now inside the loop, and that forces the phase error to be a non-zero value. But that bias in the first order loop serves a very important purpose. It's getting amplified by the loop amplifier, and then it creates the DC voltage that goes into the VCO to push the VCO to match the input signal's frequency. If that didn't happen, the phase lock loop would never stay locked. It would just sit there and not do anything. Instead, we want it to track and follow the input signal in this instance. So I want to go back to the simulation and just take a look at that.
My son is walking.
We had done this model last time where, is this big enough for everybody, or should I put this in a bigger size?
I'm on my way there right now. Just patrolling for eyewitness.
Okay, I could do that, make it a little bit larger, but then I have less on the screen. So I'm probably going to make it smaller again, just so I have a little bit more real estate on here. Okay, so we were putting in a frequency step that turned on. The step frequency was 8 hertz, so that means we're putting a linear phase ramp. So 2 pi times 8 gives you the linear phase times t, but this is the frequency that we first hit the loop with. At 1/2 second into the simulation, we hit it with an 8 hertz frequency offset. Then at 1.5 seconds into the simulation, we bang it back in the other direction by 12 hertz. So the net is 8 minus 12, which is minus 4. So as time rolls on, it's being pushed 4 hertz below its quiescent frequency. And because this is what's known as a baseband simulation, we don't really ever see the carrier frequency in the simulation model. And that's really reflective of the first block diagram we were looking at. This is the so-called baseband phase lock loop model. All we see as the input is the input phase deviation on the carrier, and then we don't see the VCO output. We see the phase deviation on the VCO output. We're going to move on and be looking at the complex baseband phase lock loop here, and then another one I have in the notes is a full up carrier-based phase lock loop, but we'll see why that's not done very often, because it's very intensive from the simulation standpoint. And of course, we linearize the loop along the way, so we could use Laplace domain analysis to look at it as a feedback system and do linear systems theory work with it. But I got off the page where I wanted to be. I wanted to be right there. So going back over to here, we pop up to 8, and then we bang down by minus 12, which nets out 4. So this was when the loop is staying locked. It comes along at 1/2 second, and the loop responds by rising up with the first order system time constant, settles at 8 hertz. And that's correct, because the VCO in this particular loop model is designed to have a KV of 1. The VCO sensitivity is effectively 1 hertz per volt. So I have to put in 8 volts into the VCO to make it tune up by 8 hertz. And then when the minus 12 comes along, it bangs down from 8 to minus 4 and settles. So that we talked about last time. That's the obvious stuff about the phase lock loop. But if we go ahead and plot the phase error psi inside the loop, we're going to see something that looks like this. So we're going to see that the error rises up, and that has to happen in the first order loop, because we have to produce a positive error to go through the loop amplifier, which in this case is 1, or 10, I mean. What is it? It's not 10. Well, it has to go through the loop amplifier to drive the VCO 8 volts. And then down here it has to drive it to minus 8 volts. So this steady state phase error is psi. The value that actually gets through the loop is the sine of psi. So that's why this is not 8 and why this is not, or 0.8 and why this is not 0.4, minus 0.4. But if we wanted to see exactly what that steady state phase error is, we would find the arctangent. And the arctangent in this case is of the delta, let's see, make sure I get my notation right, the delta of omega, which I'm putting in just in hertz, divided by the loop gain all the way around, which is 10. It's actually 10 times 2 pi radians per second, but there's 2 pi in numerator and denominator that cancel out. So that is the 0.92 that we see up above here. That's that value. And then when it's sitting down there with the input frequency at minus 4 hertz, the phase error is going to be the arcsine of minus 4 over 10, and so on. So that's where those numbers come from. How do I know that's true in the loop? Well, the way the loop is set up, the way I enter parameters in here, I get to put in the cutoff frequency of the loop, which in this case is kT over 2 pi. Fn is kT, which is the lock range in radians per second, divided by 2 pi for the first order loop. Remember, we had the math sitting there, which I guess is easier to see over here. Well, we have this right here that just shows us the lock range, and we did our linear model down here. We got to see that kT was the cutoff frequency of the loop's low-pass filtering action. So this should now make more sense. The VCO is doing exactly what it needs to do to match the input, and then the phase error is slightly different through the scale factor and then through the arcsine because of the phase detector. What I could do here in this simulation, just to let you know that if I fully linearize the loop, I could set this last argument, which toggles between linear and nonlinear. If I make the loop not have the sine phase detector in it, but just a linearized version of it, I put in 0, run my simulation, I get the same output, but now if I calculate the phase error, it's going to be exactly 0.8. Fn for the loop is 10, so it's 10 times 0.8 to make 8 over at the control voltage side of the loop, and then minus 4 for the control voltage. So we're getting different values only because we have the nonlinearity present in the loop, the real phase detector. Let's see. Okay. We talked about phase plane. I think last time we talked about driving the loop out of lock, so that if KT or Fn equivalently, because that's going back over here to this, well, let's see, the notion over here. The loop gain effectively in hertz rather than radians per second is kT over 2 pi. When we do that, that tells us that the lock range is plus and minus 10 hertz, because that was the math that we had over here in the notes. This equation right in here talks us about the total lock range. We can bring the input frequency above and below the carrier by kT, and if we divide that by 2 pi, that's going to be in hertz as opposed to radians per second. So what I was doing when we were leaving class last time, I was pushing it harder than what the loop can handle. And here I'm putting in a 12 volt frequency step when the loop gain in hertz is only 10. So the phase error shows it slipping cycles the phase is just ramping like crazy because it can never find a lock point because the phase plane plot is not crossing through 0 ever. And if I look at the VCO control voltage, it rises up, hits 10, that's the maximum that can go into the VCO based on the gain of the loop, and it's still not high enough to get to 12, but the loop just can't catch anything to make it go higher, so it just slips a cycle and then drops back down and then comes back and tries again. So if you were this phase lock loop, it would be like running, trying to grab onto something, and you just keep, well, maybe a better analogy would be jumping up and down trying to reach something that's out of your reach, and you just would do it over and over again, and you'd get exhausted trying to do that. I don't know if that's a good analogy or not, but the loop is trying to desperately to get locked, and it's outside the lock range. And I think I showed last time, if I get this right down to 10, it will just hold on by a thread. Because this is a computer, it will pull in, and this steady state value, the phase error, is now the maximum that the value can be, which is going to be pi over 2. Just verify that. .57, so that's what this number is right here. I guess if you didn't believe me, I could go look at psi itself, which I plotted, and then take the last value like that. It's not quite minus 1.57. I guess because we didn't run the simulation long enough for it to rise up finally in steady state at 2.5 seconds. And if I then replot the VCO control voltage, it does manage to rise up and get to the 10 volts. But it's just holding on by a thread. Doesn't really have any margin for error. If you were experimenting with this in the lab, you would just barely touch the frequency of the generator that's inputting into the phase lock loop, and if you touched it at all, the loop would pop out of lock because it's just barely able to hold on to that. So now we're going to go over and look at the second order loops. We're going to look at the math behind that, and this will be using the linear model. Come back and spend some more time with this stuff for the simulation problem in the homework. But what I'm going to do now, this is a simulation I have in the notes, which the one in the notes was done in MATLAB, but then we looked at the one in Python. Both simulations run the same way. An integral is the integration that's required in the loop is done using the trapezoidal rule, which is talked about right here. And Dr. Zemer has that discussed in the book as well.
You know, I was going to ask if it weren't important. Don't make me beg.
That look is
So now we're going to look at a very popular second order phase lock loop. The first order phase lock loop has problems. One problem is it has to produce, it's always going to have a static phase error or a steady state phase error to tune to a frequency that's not the quiescent frequency of the VCO. And in most applications for coherent communications, that's not acceptable. We don't want any static phase error or steady state phase error. So control systems people are familiar with this issue as well, trying to get the error to go to 0 essentially. And we can do that by putting in a loop filter now that has an integrator in it. So the integrator gives us effectively infinite DC gain, which means we can drive that steady state phase error to 0. But because we now have an integrator in the VCO itself and then the integrator in the loop filter, that nets us out 180 degrees of phase shift around the loop. And since we're already using negative feedback, if we put in an additional 180 degrees with negative feedback, then we'll have positive feedback and our control system will become unstable. So what we need to do is put in what's called lead compensation, which is the 0.
So what you got?
So that's going to advance the phase and pull it away from ever getting to 180 degrees or minus 180 degrees of phase shift. This will stabilize the circuit. And if you can think back to circuits, you can remember that for second order systems you would have 3 different cases. In a second order system you would have overdamped, underdamped, and critically damped. Usually in a phase lock loop, the design is done to make it be underdamped. The underdamping is desirable because that way the loop has faster response. It has some overshoot and undershoot, but it's just a more desirable configuration to get a faster response. The overdamped situation is where the 2 poles, due to the second order system, are on the real axes. And critically damped is when the 2 poles are on top of each other, and then underdamped, if you remember from circuits, is when the poles are complex conjugates of one another. So they're sitting in the left half S-plane. So that's the situation that we're going for. We're going to be going for, if I draw the S-plane here, sigma j omega, we're going for that situation where we have a complex conjugate pole pair. A related loop filter is the one shown here. This is in text problem 428. This is called the lead lag loop filter. This was popular when I worked in industry and we used op amps to make loop filters, and we didn't want to have an perfect integrator because the perfect integrator has issues with drifting off if there's a bias in the op amp. And it seems to me that you ought to experience that, and I guess a question I have is, in electronics, at some point so far, have you hooked up an op amp to be an integrator? In other words, have you ever tried to do something like this?
Well, he's up.
He's been up for hours.
I know, I missed you too.
This is the minus input. Has anybody ever hooked that circuit up in the lab?
I know, it's just, I killed a man in front of a witness. I just had to tranquilize to keep her from scratching my eyes out.
What?
Okay. In an LT Spice, if it was a perfect op amp, it still was okay, but if it wasn't a perfect op amp, what did the output do over time?
And I really like him, which is what pains me so much about this, but he needs a reliable pair.
It should have run off to the rail, a power supply rail, like positive or negative voltage or something like that.
It'll never happen again.
Do you think?
Because there's always an offset voltage in an op amp.
Never lie to someone who trusts you. Never trust someone who lies to you.
Yeah, I know.
Genuinely.
Well, just thought maybe you might remember that. So the loop filter that we're actually looking at, though, so the 2 loop filters that in the analog domain that people would build for phase lock loops would be, I'll draw them out here and then modify them. So let me see. Didn't want to erase that, though.
That's right. There's no point. I thought you were a clown. No, I thought you were doing an end run on steakhouse procedures.
That's R1, R2, and C. So that's that loop filter implements this F of S that we have right here. And then the F of S, the second F of S we have here, is implemented in this fashion by putting a resistor in the feedback path and not having infinite gain anymore at DC, because there's now a resistor in there, right? The gain at DC is now R3 over R1. It's actually minus R3 over R1, but so those are some ways that analog phase lock loops would could get a loop filter built with an op amp. At any rate, going back to the integrator with lead correction, as it's called, so that's down here, we just go to the closed loop gain expression that we had developed earlier. How earlier? Well, that was way up here, but we did do it last time.
And may I thank you for getting the lazy ass off the couch and joining us. Thank you. It's a typical of us, and we have reason to believe it was handled by one of us.
There it is right there. So we're just dropping in a different value of f of s. Before we put in f of s equals 1, which is what I call a wire for the loop filter, no loop filter. So now we're putting in this lead lag filter. Drop that in, do some algebra on it, and we get this is the form after algebra. So we have a 0, and then we have 2 poles. So we have a rational transfer function of that form. We can also get a transfer function that goes from the input to the phase error psi of t. So that's, in the book, that's called g of s. And if you compare that to h of s, you see that this is the relationship. The loop error transfer function g of s is 1 minus the closed loop transfer function h of s. At any rate, moving down to this next bullet, in circuit theory and definitely in control systems, you see a second order denominator like that, and you say it can be written in a standard form, which would be s squared plus 2 times damping zeta times omega n plus omega n squared. So those are just the traditions in the business of looking at that. So for this phase locked loop model, we have omega n, the natural frequency of the second order closed loop system, is square root of kt times a, just by noting that. So you square root that to get omega n. And then you can solve for the damping as the center term, which is kt, divided by 2 times omega n, and then that gives you the expression after you simplify the algebra. So we have the damping in terms of kt and the lead correction a, and we have omega n. So generally, this is the analysis equation. Generally, if you're building a phase lock loop, you're interested in the synthesis. And so what do I mean by that? Analysis says we put in the values that the loop has got in it, the kt and the a from the loop filter, and we are able to see what omega n value and zeta value we have. If we're doing a synthesis, like we're going to design a phase lock loop, we might say we want 1 kilohertz or 1 kiloradian per second for omega n, and we want a damping of 0.707. So then we come out with the equations that tell us what kt and a need to be. In the phase lock loop class that I've been teaching all semester, those are the types of things that we did and have done. In this class, don't get that wrapped up in it, because this class is not a majoring in phase lock loops. But I'm just letting you know that that's how that would work. What we are interested in doing right now, though, is seeing that for the second order phase lock loop, and this is also known as a type 2 loop. Type 2 means that we have 2 integrators in the closed loop system. We have an integrator due to the VCO and one due to the loop filter. So for a type 2 system, one of the properties of the type 2 system is if I put in a frequency step into the input of the type 2 system, or a step of some sort into the system, or actually it's going to be a ramp, never mind a ramp, so it's a frequency step with respect to phase, the steady state phase error will go to 0. And the way we do that is we go, what's going on right here, and I guess I didn't put in all the details, we have Well, we're interested in
Serious fever. I'll bring that down. I'm not trying to drug you, though. They're just antibiotics.
limit as t goes to infinity of psi of t when
Dehydrated.
phi of t is equal to 2 pi over delta f. Yeah, 2 pi delta f. Got too carried away there. So in order to get our hands on that, we decided to use the final value theorem, something that, I don't know, you learned about that. Which class do you remember that? Learning that, 3205? I'm just curious. I know, Chris, you learned about this in control systems, but don't you learn about it in 3205? Or maybe it's in 2205, I don't know.
I'm not gonna hurt you, I just want to see you get better.
Okay. Well, you're the 1 year older in the program than most everybody else in the class. What are you guys that had it last semester? Do you remember the final value theorem?
You saw me.
Okay. Well, it's cool. It's powerful. Rather than having to take the limit as t goes to infinity, we can just take the limit as s goes to 0. So we take s times psi of s. So that's what we've got inside of here. This is, in the s domain, that's psi of s, which is going to be equal to the input, which is delta omega over s squared times g of s. But remember, up at the top of this page, we said g of s is 1 minus h of s, the closed-loop transfer function. So that's what we've got inside the square brackets here. And then when you take the limit, you get a convenient cancellation in here. That goes away. There's still that s, which is part of the final value theorem. But as s goes to 0, everything is now cool. This is 0, that is 0, and we get delta of omega times s over kt times a, but it's still 0. So that means the steady state error goes to 0. I'm going to spend a little bit more time with the final value theorem for different types of loop filters and then different types of dynamics. I say dynamics because in the world of satellite communications or vehicular communications, we've got the transmitter and receiver are generally not moving at the same velocity. In the case of a satellite, we have a ground station and we have a satellite up in space, which does have motion associated with it relative to the Earth. In the case of the base station, cell tower, and you driving your car around, there's dynamics there too. You've got a velocity, and whenever you have motion like that, you've got something that you learned about in physics. You've got Doppler, right? You got a frequency shift due to the fact that you've got velocity involved between the two platforms. And in general, we worry about phase step, a frequency step, a frequency ramp, and then a parabola ramp, I guess. So in terms of physics, we have things like jerk and jolt. You might remember that from when you took physics. Those are the higher order derivatives associated with position. You know, it goes position, velocity, acceleration, jerk, and jolt, if I remember right. Does anybody remember that from physics?
Lumen doesn't trust me because of the truth.
Well, just having two cars pass each other, there's those platform dynamics that go on, and In my phase lock loops class this semester, they had a problem on their midterm where they were studying a flyover situation. So it was a plane is flying overhead, talking to a ground station. What is the platform dynamics associated with that, and loop tracking? So they were playing with that. Another thing that's nice to understand about the higher order loops is what sort of transient do you have. So when you have a frequency step into this second order loop, we like to be able to see what the actual phase error is doing as a result of delta of omega. And this is assuming a linear model, but this transient is this equation right down here. So it's something that would be the inverse Laplace transform would get you that. And there's a lot of other combinations out there for different types of loop filters, but this is a pretty standard one though. So it's a damped sinusoid is what it is. So now we're going to look at a simulation in Python. I'm pretty sure I have it in MATLAB in here, but the Python one is the one I can play with. So this particular simulation, we're going to go through the synthesis equations. Synthesis equation means that I come up with KT given zeta and omega n, and I can't come up with A given zeta and omega n. So this is how I would actually design a phase lock loop given requirements that might come from my customer or the needs of the system. So I plug in some numbers. In this case, I'm wanting a damping of 0.707. I want the natural frequency in hertz to be 10 hertz. So I come up with these numbers, 88.84 and 44.43. And then we're going to input a frequency step. Here I was doing 40 hertz. I'm just going to jump over and look at it in Python though, and you can look at the simulation here in MATLAB code or see how I did it in Python. So we're going to set up just a frequency step. In this case, I've got a number in here. It looks like in that example I had 40, so I'll put in 40 for delta F. And then in our phase lock loop simulation function, PLL1, we just have to go inside of that and hit Shift Tab to see what the arguments are. So theta is, I put in as phi. Theta is just the notation when I wrote this, and is to match our book, it's phi. Put in a sampling frequency, which should be at least 10 times more than the highest frequency. I'm trying, or well above that, so I'm putting in 1,000 hertz. I'm putting in the loop type, so when I set loop type equal to 2, I'm going to get the integrator with lead compensation, which is the one we were just talking about. And then I get to put in KV, the VCO gain, but I typically will just set KV equal to 1, so that way I get the signal that's present at the input to the VCO will exactly reflect the frequency that the VCO is tuning to. So I'll set KV equal to 1, and then the next input is the natural frequency Fn, which is omega n divided by 2 pi, so that's 10. That's exactly what I wanted in this problem. And then I'm going to put in the last parameter, almost last parameter is the damping zeta, and then whether I want linear or nonlinear. We were using the same function moments ago, but we had this argument set to 1 for the first order loop. So I'll run that. I'm going to plot the phase error in this case. I'm not going to plot the phase error. I'm going to go over here and change it to plot the control voltage because that makes more sense initially. So I'm putting in 40, and we see the loop does lock. The control voltage rises up to 40 to match the input, We also see a phenomena where the loop is having to slip cycles to eventually pull in rather than just being a smooth transient. If I make this a smaller frequency step, like 10, it rises up like a linear system and just has some overshoot and undershoot, but it comes right in. But in the case of this large a value, we're exceeding the lock range of the loop, so it has to pull in gradually, and this creates a rather interesting phase plane characteristic. I'm not really going to study the phase plane, but I do have a plot of it that we can do down here. It starts here, and then what it's doing is it's slipping a cycle, slipping another cycle, but it's moving down, getting closer to pulling in, and then it slips another cycle, and then finally when it pops around and has to go one more cycle, it's finally able to get close enough and just quickly spirals around and pulls in. So that's something that the first order loop cannot do. The first order loop we would have never locked, so we would have been outside the lock range. But here it's able to do that. If I push it harder, in other words, make it acquire from further away, it's just going to slip more cycles before it pulls in. But it does indeed pull in. Now there's some other interesting things I could do with that, and that is if I want to put in a 40 hertz frequency step, if I was to change the natural frequency over here to say 20, then the loop's going to respond faster, and now it doesn't require any cycle slipping because the time constants are much smaller by a factor of 2, and the loop can pull in naturally in one cycle, and that's what we're seeing happening here. On the other hand, if I make the natural frequency less, like 5 instead of 10, now it takes even more cycles to pull it in. Let's go back to 10, and let's go back to 10 over here. So this pulls in a fraction of a cycle, and if I now plot the phase error, I'll get this shape right here, and this is, I think I had a zoom factor on here for that. This is a damped sinusoid, so this is the loop getting that frequency step. It jumps up and produces an error. That error gets integrated in the loop filter, but it's like thrusting the VCO to produce a voltage through the integration of a large number, and then the integrator in the VCO in the loop filter holds that value, and it charges up, and it's able to push the VCO, and then as a result of pushing the VCO, the error comes down, and it can settle back to 0. So this characteristic right here is exactly this curve. It's exactly this guy right here. If I put in 2 pi times 10 hertz, put in the natural frequency 2 pi times 10 hertz, and put in a damping of 0.707, that plot we're seeing there is this, mathematically speaking. So that's the loop pulling in, and this is a fraction of a cycle pull in because we're within the lock range, or I'm trying to think what the right term is. It's part of my phase lock loops class, but my brain has slipped out on that momentarily. What I want to do, though, before I actually go on, and we only have 5 minutes left, I want to talk a little bit about this, but since I had this slide up here from my phase lock loop class from yesterday, the phase lock loop class is now looking at synchronizing onto digitally modulated carriers, and we're doing it using a complex baseband simulation model. So this is carrier phase syncing that we're doing here, and in this particular case, I have noise added to the system, and I don't have any frequency error at this point, but this is just showing you how the loop has to pull in. If I put the frequency error back on here, which I think was some number like 0, 1, I'm not positive what I had this set for. I have this waveform, or this scatter plot I call a donut. This is the carrier signal is spinning around in the complex plane, and there's noise added onto it, and that gives it width. That makes it more like a donut. And phase modulation, like we've been describing, is used to send 8 different phase values, which with 8 different phase values, how many bits of information can that carry per phase value? Log base 2 of 8 is what? 3? So we have 3 bits per symbol in this system of digital modulation. The loop pulls in with the noise. In this case, it's too far away to pull in naturally. It has to slip some cycles, and that's what it's doing. And then it locks up, stops the waveform from spinning due to the frequency error, and then we can make decisions on these 8 phase states. Another scheme down here that I did an example of yesterday was 64 QAM, quadrature amplitude modulation. This is also spinning due to a frequency error. The loop pulls in. This transient response looks very much like what we're just looking at because it's the same type of loop filter. And when it locks up, in this case, we get 64 different modulation points. QAM is what you're going to be studying in project number 2. QAM is used in our cable modems. It's used by DOCSIS. DOCSIS stands for Data Over Cable System Interface Standard. And if you have Comcast, you have purchased a cable modem, or maybe you're renting a cable modem, and it sends very high density modulation so that we can pull down a lot of bits per second per hertz of bandwidth in our homes. That's what I'm using in my house. So phase lock loops are part of synchronizing in digital communications waveforms. You won't be doing synchronization in your project, but my phase lock loops class is doing that right now. You're just going to be doing static, no significant errors in the modulation to impair it. So I want to look a little bit at what you're going to do with this simulation. And so I'm done with this, done with all of that. This is an example of using a complex baseband phase lock loop to demodulate sinusoidal FM, and that is what the homework problem is doing. We will be getting up to frequency synthesizers, so we're just very close to that. If you want to read ahead over the weekend and see how this works and how the synthesizer works, that equation right here is kind of all there is to it for this synthesizer. There's not a whole lot to it. But I want to just briefly, let's see, wrong problem. I want to briefly talk about what you're doing in the second problem you're going to turn in. So I'm going to want you to set a loop up, a first order loop and a second order loop, do all these parameters, and then you're going to put in sinusoidal modulation of varying frequencies so that you can estimate the recovered modulation amplitude EV that's at the output of the loop filter before you go into the VCO. And I describe the mathematics behind that down here. You're basically striving, and you're going to do a theoretical comparison to make a measurement of the magnitude of the control voltage, which you can define in terms of the loop transfer function, magnitude of h of j 2 pi fm, the magnitude of the phase, which is 1, and then the amplitude that you measure, and then the deviation constant of in the modulator and the VCO gain constant KV. So the way you're going to end up doing that is this complex baseband phase-lock loop simulation, which allows you to put in an actual modulated carrier. It's just going to be a complex sinusoid carrier. So the modulation is sitting right here. This block diagram is from my phase-lock loops class, so this should say phi from our notation, but it says theta instead. And then the VCO is a complex sinusoid-based VCO instead of a real cosine. And the phase detector, instead of being sine, is the imaginary part of what comes out of this complex multiply. But other than that, the other components are the same. We have an effective gain K, we have a loop filter F of S, we have a 1 over S due to the integration action of the VCO. And so if we run a simulation, which in the interface is pretty much the same after that, if you run a simulation, like I've got over here, I'm going to do 2.5 seconds. I'm going to have the carrier frequency of 0 rather than having it step to some value. The carrier frequency will be at 0 in the complex baseband sense. The amplitude of the modulation is 1. The FD, peak deviation for the modulator, is 1. The FM is 1 in this case. And so here's my message, phi, directly FM or angle modulating the carrier, and here's the carrier, 2 pi times F naught times T plus phi. And then it goes into our complex baseband simulation, which is pretty much the same interface, like I said. Rather than being phase, though, this is actually a complex sinusoid signal, sampling frequency, the type of loop, the VCO gain, which I'll set equal to 1, the natural frequency in hertz, and then the damping factor. So when I run this simulation, the loop goes through a transient as it's locking up, but then it's producing a nice smooth sinusoid. This is what you're going to be interested in measuring in that problem. You're going to be going after the peak amplitude when we've gotten into steady state out over here. And if I change the message frequency, say make that be 10 hertz, the loop is just responding to a higher frequency now. So the cycles are closer together. The peak value is different, but you'll be characterizing that in this problem. So this is the little test bed in the problem. And this is the theoretical calculation right here for the first order loop. This is an experimental test bed for both the first and second order loop. So this section of the notebook is where you do all your measurements that you use to produce the results asked for in problem 2. We are out of time, past time. I'm ready to wrap up though. It looks like it stopped snowing out for the time being as I'm looking into my backyard. Anybody have any questions before I shut down? Yeah, I will. Yeah, you'll have them. I just haven't put them up there yet. That's a week and a half away. But yeah, I'll do that. I'm running hot and heavy on everything because as I'm just like you guys. I have 3 classes, and you got maybe more than 3 classes. I'm sure it keeps you busy all the time. I was working on a radar model today to try to help that radar team out. I haven't spent a whole lot of time helping them with their issues, but Capstone Design is running in the background for you, Chris. Yeah, that's the most disappointing thing for the whole semester, right? Capstone Design had to make a major right turn as a result of... Yeah, everybody's got an issue like that. Both the teams I'm working with, they're struggling with that. Any questions related to this class, though, for right now? I know I've gotten some homework turned in already. I'll be looking for them though later on Slack. And people have pushed me their papers. So I'm also thinking about revving up Project 2 just so that you can have a chance to look at it. So I'll probably get it out there next week. It involves digital modulation, but the first part of it is related to PCM, which we've already discussed. We're not too far away from heading into the finish line on this chapter. We might even be able to finish the chapter by the end of next week. Of course, I'll be giving a review on Thursday for the exam that will be on Tuesday. Yeah, yeah. There's a bunch of application in the notes, as a matter of fact. So we haven't gotten that far yet, but I've got a number of applications, and we don't really spend that much time on the phase lock loop. It's just synthesizers, very simple math, a few applications over here. That section we skip, it's no longer in the book, but then coherent to modulator. This is the type of stuff the phase lock loops class is doing, but you don't have to do it. I'm just pointing out that it gets used for that. And then some more phase lock loop applications, and then we're done. So really, first order phase lock loop is really all you need to be a master of. The second order loop, you're doing an experiment with it, but you don't have to know anything intimate about it except being able to take some measurements in the notebook there. And then we'll move off, and then we'll head on down to finish off the chapter, which doesn't have a tremendous amount of stuff left in it. Well, I'll talk about FM stereo. So I think we're doing good. The last chapter is going to be radically different. It's going to look more like circuits. It's noise analysis. Yeah. Have a good weekend, and I'll be staying tuned into Slack best as possible. The more the weather is not nice, the more I'll be inside. Although I've already been outside walking once today, and the wind is kind of cold right now, or it was when I was out earlier. Now, is anybody psychosomatic? I keep thinking I'm getting sick, and then I get kind of worked up about it, and then I go outside and walk for a while, and then I prove that I'm probably okay, but staying inside too much makes me feel like not always feel good.